Hello everyone and welcome back again. Today I'm going to show you how to derive Arrhenius equation. This equation is used to calculate the activation energy of a chemical reaction at two different temperatures. You can see the temperatures here. We've got T1 and we also have T2. Now, how do we derive this formula and where does it come from? It all comes from this expression here. We've got K equals A. This A is simply the pre-exponential factor. It's related to the collision frequency and orientation of molecules in a chemical reaction. And E is Euler's number. And this is raised to the power of negative EA, where EA is the activation energy divided by R. R is the ideal gas constant and multiplied by T, which is the temperature in Kelvin. How do we use this expression to derive everything on top? Now let me show you how to do that in a couple of minutes. We just have to write the expression down. So we say that K is equal to the pre-exponential factor multiplied by Euler's number raised to the power of negative activation energy divided by RT. The next thing that we have to do is to take the logarithm of both sides, the natural logarithm of both sides. So we say ln K equals ln multiplied by AE raised to the power of negative EA over RT. Okay, next, what do we do here? We copy down the left-hand side. We have the natural logarithm of K equals. Now you can see right here that there are two terms that are multiplying. We've got A and E that are multiplying. And according to the laws of logarithm, if two logs are multiplying, you can simply separate them and add them. So we apply the same principle here, and this now becomes ln A plus ln E raised to the power of negative EA over RT. We simply applied the multiplication law of logarithms here. So when two logs are multiplying, you can see that this A also multiplies the E. So we assign the natural logarithm to both of them and add them. Again, we have ln K is equal to, we copy this one down, ln A. Again, we have plus. Looking at this expression right here, which is ln E raised to the power of negative EA over RT, we're also going to apply another logarithm law or principle that says, suppose you have the natural logarithm of, let's say, m to the power of k. So this m is to the power of k. We can rewrite this expression to be this k goes to the back of the logarithm, and we have k multiplied by ln m. Okay? So this only works when the logarithm is raised to a power. In this case, we can see that the natural logarithm of e is raised to a power of negative EA over RT. So we're going to apply the same principle here. And that means that the negative EA is going to come down. So we have negative EA over RT. And it's multiplied by the natural logarithm of E. Good. Okay. Now we need to understand something. The natural logarithm of E is equal to 1. This expression here equals 1. Whenever you see the natural logarithm of E, this is simply equal to 1. So this means that we have the natural logarithm of K equals ln A minus times the plus gives us a minus, and we now have EA over RT multiplied by 1. Again, we have the natural logarithm of K equals ln A then minus EA over RT. Writing this nicely, we have that ln K is equal to negative EA over RT plus ln A. Okay, so I did not really change anything here. If you have, for example, 3 minus 2, this is equal to 1. Okay, so you can see that this one is a positive, this one is a negative. If we also say minus 2 plus 3, it's also equal to 1. So as long as they're adding, it does not really matter. Okay, so this is the expression that we want, and we're going to use this to derive the equation at two temperatures. So I'm going to say at two temperatures, the only thing that's going to change are the rate constant and the temperatures. So we have ln K1, okay? When we have two temperatures, the temperatures are also going to affect the rate constant. So we say ln K1, that is for the first temperature, equals, the activation energy remains the same for the same reaction. So we have minus EA over RT1. This T1 represents the first temperature, then plus ln A. So we don't say ln A1 because A is basically a constant, okay? Now, for the second temperature, we say ln K2 equals negative EA over RT2 plus ln A. Okay, so next we have to subtract these two equations. So I'm going to subtract 1 from 2. So we say subtracting equation 1 from 2. This is our 1 and this is our 2. So we're basically removing 1 from 2. So we write them nicely and this becomes, remember we said you subtract 1 from 2. So this becomes ln K2 minus ln K1. Okay, so K2 minus K1, and this is equal to negative EA over RT2 plus ln A, then minus our equation 1, which is negative EA over RT1, then plus ln A. Okay. Remember, we have another law of logarithm that says if two logarithms are subtracting, it means you can divide them. So let's suppose you have ln A minus ln n, something like this. This can be written as ln A over n. Okay, so we also apply the same principle here to simplify the logarithm. So here we write the left hand side to be ln, remember that they are subtracting, so this now becomes K2 over K1. And this is equal to, I'm going to distribute this negative across everything inside the bracket. On the left here, or right here, we have negative EA over RT2, then plus ln A. So negative times a negative, that gives us a plus. Hence, we have plus EA over RT1, then negative times a plus, that gives us negative ln A. We copy down the left hand side and we have the natural logarithm of the two rate constants, K2 over K1 equals, now looking very closely here, we have plus ln A and we have minus ln A. So ln A minus ln A, that gives us a 0. We can simply cancel these two. And now we are left with negative EA over RT2, then plus EA over RT1. Next, we have the natural logarithm of the two rate constants, k2 over k1 equals, I'm also going to rearrange these two. Hence, we have EA over RT1 minus EA over RT2. You may be wondering, does it really work? Yeah, it works because, for example, here we have a negative and we have a plus. So if you say negative 4 plus 5, this is equal to a 1. Again, 5 minus 4 is also equal to a 1. Okay? So as long as they are adding, the order does not really matter. Next up, what do? We copy down the left-hand side again, and we have ln k2 over k1. This is equal to, now looking at both sides, you can see that EA is common, EA over R is common here. So we have EA over R, again, EA over R. So we can factor out EA over R. If we factor out EA over R, we open our bracket. So EA divided by EA, okay, that gives us a 1. And if you remove R from RT1, we have T1 remaining. Then minus, if we remove EA, if you remove EA again from here, we have a 1 remaining over, and again, if you remove R from here, we've got T2 remaining. So this is Arrhenius equation, the equation used for calculating the activation energy of a chemical reaction at two different temperatures. So when you get to this final stage, you can simply factor out. So we say factor out EA over R. If you factor out that out, you're going to have 1 over T1 minus 1 over T2 remaining. And you need to understand that if, for example, you have a K2 on top here, then T1 must come first. If you have K1 on top, then T2 must come first. Don't forget. Thank you. I believe this video has helped you. If it has, please subscribe and like this video. Thank you and see you in the next video. Bye.